Hi there. In this video, we're going to talk about how to calculate residues. We had seen in the last video something called the Laurent series, and the Laurent series was written as is on the screen right now, where we had some terms in which the exponents were negative and positive. And this was specifically for the region in which we wrote our circle of convergence with a singular point inside the circle. So then we looked at what happens when we integrate this function around a contour written in the form of the Laurent series. We then see we integrate each term of the Laurent series, and when we do that, we find an interesting result, which we had seen in the last video, that all of these terms go to 0 except for the term with the -1 as the exponent. Okay, so all of these terms go to 0 except for the one with the -1 exponent. So this integral just becomes 0 plus 0, then plus this integral with the -1, which takes on the value of j times 2 pi times this coefficient a minus 1 and plus 0. Okay, so the integral of this function only takes on the value for this particular term, which is this. And the residue was this coefficient a minus 1. So this has lots of applications in the sense where we can evaluate a very difficult integral in which we have a singular point within this circle of convergence, and it merely takes on the value of this integral if we can find this coefficient a minus 1. So we're just going to illustrate that with a simple example in which we have this radius of convergence, and we want to find this coefficient a minus 1, or we want to find the residue. So the function that we are considering is fz is equal to z over z plus 2 times z plus 4. So we are integrating this function along this contour, and it's a circle of radius 3. Now, the question here is, how does residues help us? Okay, firstly, to even write the Laurent series, this circle of convergence must be present in an annular region. So there must be an annulus between this contour, right? So we could say, for instance, that this annulus, this contour could be between the annulus, where z is between 2 and 4. Okay, so if we were to draw z being more than 2, the circle z is more than 2, then it probably might look like this. Okay, and then z less than 4, maybe that might be outside here. Well, it is outside here, like that. So we can see now that our contour is inside this annular region. So that's good. That is what we want. So we can now expand this function in terms of the Laurent series. So the first step that we're going to do is we're going to take this function and split it up to be in partial fractions. So we'll say that z over z plus 2 times z plus 4 is equal to 2 over z plus 4 minus 1 over z plus 2. So that's what we get when we split up this function to be in terms of partial fractions. So now, if z is more than 2, which is this first part of this inequality, so if z is more than 2, and we have our term here, which is 1 over z plus 2, what I'm going to do is I'm just going to rearrange the denominator a bit, in which I will take out z as a common factor. So if I take out z as a common factor, then I get z into 1 plus 2 over z. Well, how does it help me? It helps me because I can write this expression 1 over 1 plus 2 over z in terms of the binomial theorem. Okay, so let's just bring that down. I have 1 over z into 1 plus 2 over z. So just a reminder of the binomial theorem. Okay, so the reminder of the binomial theorem, we have 1 over 1 plus x. So that's the same as 1 minus x plus x squared minus x cubed plus x to the 4, and so on. It carries on like that. So that's all I'm going to do. I'm going to write 1 over 1 plus 2 over z in this same form, but instead of x, I will have 2 over z. So this 1 over z, I keep the same. So then I write this as I've indicated here in this expansion. So I have 1, that's the first term, then I have minus, then 2 over z, then I have plus, then 2 over z squared, so that gives me 4 over z squared, and then the next term is going to be minus, then I'll have then 2 cubed, which is 8 over z cubed, and I can write it for each of the terms thereafter. So I can just expand this out, or I can multiply each term by z. So if I do that, then what I get is 1 over z minus 2 over z squared plus 4 over z cubed minus 8 over z to the power 4. And it would carry on like that. So I've done this for this expression. Now I can do it for the other term, that's 2 over z plus 4. So if z is less than 4, which is what we had said in this circle, there's our contour, there's the values of z, and we said that z is less than this red circle 4. So since that is the case, we can now take that expression 2 over z plus 4, and we can take out 4 as the common factor in the denominator. So I have 2 over 4 into 1 plus z over 4. 4 times 4 is 4, and 4 times z over 4 is z. So this 2 over 4, that is just 1 over 2. So I can write that as 1 over 2. So I can take this and expand it in the binomial series, binomial expansion, as I done with the first expression. So I have 1 over 2 into 1 plus z over 4. And if I expand that out, I get a half. And let's just remind ourselves, I think I erased it, but never mind, I can write it again. 1 plus 1 over x, that's just equal to 1 minus x plus x squared minus x cubed, and so on. So the first term is 1, then we have minus x, so it's z over 4. Then the next term is going to be x squared, or z over 4 squared. So I'm going to have z squared over 16. Then the next term is going to be cubed. So I'm going to have z cubed over 4 cubed. So 4 cubed is 64. And it would carry on like that. So I just multiply this out. If I multiply that out, I get a half. And a half times z over 4 gives me minus z over 8. Then a half times z squared over 16. So I'll have z squared over 32. And then minus z cubed over 128. And this would carry on. So I have this expression, which is the partial fraction, corresponding to this one, subtracted by 1 over z plus 2. And we said that 1 over z plus 2 is this particular expansion. What we're going to do is merely take the expansion for 2 over z plus 4, and we're going to subtract it from the expansion of 1 over z plus 2. So our original function, which is z over z plus 2 times z plus 4. So that is equal to 2 over z plus 4 minus 1 over z plus 2. So this is the first series expansion, which is 1 over z minus 2 over z squared and so on. Oh, sorry, this was the first series expansion corresponding to this term. So that's a half minus z over 8, that's z over 8, plus z squared over 32 minus z cubed over 128. So we're now subtracting this, okay, and of course this carries on. So we're subtracting that from 1 over z, here's it here on the top, 1 over z minus 2 over z squared plus 4 over z cubed minus 8 over z to the power 4, and so on. So if we actually subtract this out and we carry on with this, then we can just write these terms first, and of course the sign of each one will change. We can just start off with the end. So we have plus, carrying on. So we have 8 over z to the power 4, and the sign will change because of the minus. So we have 8 over z to the power 4. Then we have minus 4 over z cubed. Then we have plus 2 over z squared. We have minus 1 over z. And then writing the rest of these terms, we have plus a half minus z over 8 plus z squared over 32 minus z cubed over 128. And this will continue. So this is kind of our Laurent series. Okay, so let's think about what we have. This term would correspond to z minus z naught to the minus 4 times a to the times a minus 4, and so on. And here we would have a minus 2 z minus z naught to the power minus 2. And then this term here would correspond to a naught. Then we would have a1 times z minus z naught to the power 1 plus a2 z minus z naught to the power 2. We can see that these terms correspond like that. Okay. So we integrate this. That's what we want to do. We want to integrate all of this. And we saw that in the Laurent series, when we integrate this function, okay, so what we're going to do now is we're going to integrate around this contour in this diagram we had drawn earlier of z over z plus 2, z plus 4. So when we do that, we had seen that all of these terms become 0, besides the one associated with the exponent to the minus 1. And we had seen that this gives us j times 2 pi times this residue a minus 1. And just looking at this series, okay, obviously z0 is 0 here. So this exponent where we have a minus 1, that's actually equal to minus 1. So there's it here. That's what our exponent is. That's what, sorry, not exponent, coefficient is. You can see it's minus 1. So this integral around this contour is equal to j 2 pi times minus 1. So we can just write a minus in front of it. So that's this integral evaluated. But we can see that this was not a very good methodology because it was quite a lengthy procedure to find this Laurent series. So in some instances, we can actually look at a shortcut to try and find the residues. So we have a shortcut. And this is applied to poles. So if the singular value is poles of order n, then we can apply the shortcut. So what we do is we take our function z, okay, then we multiply it by z minus z naught to the power n, okay, and then we take the derivative of n minus 1 of this product that we had just seen, and the denominator is dz to the n minus 1 since we're taking the derivative. And then we multiply it by 1 over n minus 1 factorial. And then we take the limit of this entire thing. We take the limit as z approaches z naught. So what does this give you? It gives you the residue. That is what this expression gives you. So we can see this illustrated in a simple example. So let's just say we have fz is equal to z squared over z plus 2 squared. So this is a pole of order 2. Okay, we can see that the 2 there is in the exponent. So this is a pole of order 2. And we can apply this expression to find the residue. So a minus 1, the residue is firstly equal to, we take our function fz, so that's z squared over z plus 2 squared. Also, this pole is the singular value where z is equal to minus 2. So that's where the singular value is. So then we multiply it by this z minus z naught to the power n, and z naught is the singular value, that's minus 2. So instead of z naught, we put in minus 2. So then we're multiplying it by z plus 2 raised to the power n, so squared. So essentially we are cancelling the denominator of this function. And we're taking the derivative of this, whole thing. dz, so n minus 1 is 1, so it's a first order derivative. And we're multiplying this by 1 over n minus 1 factorial, so n is 2. So we can just substitute that in, and we can just say 1 over 1 factorial. This entire thing, we're taking the limit as z approaches minus 2. So let's simplify this. That and that will cancel. Okay, so we have the limit as z approaches minus 2 of essentially d dz of z squared. That's what all of this comes down to. So that is the limit as z approaches minus 2 of 2z, which is just minus 4. So this is what the residue is. And you can see that this much simpler approach, the shortcut for this particular scenario where we have a pole of a certain order, gives us a very simple way of determining the residue of a function. So thank you very much for watching.